This video will be covering section 8.3, separable differential equations. We have two objectives. We're going to start by solving differential equations that have this form. This is what we mean by a separable differential equation. And then we will finish with application problems involving separable differential equations. Okay, so what is a separable differential equation? Well, it's a first order differential equation, meaning that the highest derivative that it has is just the first derivative. And that first derivative can be expressed as the product of a function of x multiplied by a function of y, which is what you see here. We have the derivative is equal to a function of x multiplied by the function of y. The reason we call this separable is that we can separate these two variables. We can move y to one side and we can move all the x's to the other side. So in this particular example, what you'd have to do is you'd have to divide by the f of y, and then what you can also do is multiply by this dx. So what it turns into is 1 over f of y dy equals g of x dx. So this is what we mean by separating the variables, moving all of the terms that have x in them on, move all that to one side and move everything with a y to the other side. Okay, why is this helpful? Well, suppose we have a separable differential equation and we do the same process that I just went through, except at this stage here I'm not going to multiply the dx over. Let's take a closer look at this piece right here. Suppose that y is, I'm going to call it h of x. Right? Remember, we can't use g or f because they're already used in this, but let's just say that the solution to this y is h of x. Then y prime, actually, sorry, let's not do that. Then the differential of y, if we remember, dy is defined to be h prime of x dx. But h prime of x could also be written as dy dx. So you'll notice that right here, so the idea is we're going to try to integrate both sides of this. So when I integrate on each side with respect to x, right here you see that dy dx sitting there. And with what we showed right here, dy dx is really, or sorry, dy dx times dx is really just dy. This can be replaced with dy. What we're really doing there is a change of variables. Technically, it's really a u substitution. It's equivalent to doing a u substitution. You could also kind of naively just think of it as you're canceling the dx's, even though there really is more going on than that, but that's where we just get the dy. So now you can see the variables have been separated. We have an integral with respect to y here and an integral with respect to x here. Now, to finish the problem, we will just actually integrate both sides. We're not going to keep showing all of those steps, so when we do this, we're going to write it more like what I had before, where I had it as dividing the f of y over, so it would have been dy over f of y, and then multiplying the dx to the other side, so g of x dx. So we're just going to kind of treat it almost like it's a proportion in a sense, and we're just cross multiplying, and then we can come in and do the integrals after that. Alright, so let's analyze whether or not a differential equation is separable in the first place. So the idea being, can we get it into a form like this? Well, the way to tell is that you should have only a first derivative, which we do on this, but then over here it needs to be a product of x and a product of y, or in this case a product of t. And we can see this one is not. There is no way to move all of the terms to just one side. You might say, well, sure you can. You could subtract that y over, so you have dy dt minus y equals t, and then you can multiply by dt. Well, but the problem when you do that is you're going to get a dt on this term right here. So you can't actually separate them. So that first one, not separable. So we just wouldn't know how to solve that right now. Okay, the next one. This is already set up as a proportion. So what we could do is we could try cross multiplying at the beginning. So let's just do that. T plus 1 times dy equals ty dt. Well, we've got y's and t's in the wrong places. So what I need to do is I need to divide by this t plus 1 on this side, and then I need to divide by y over here. So we end up with dy over y equals t over t plus 1 dt. So this one is separable. Right, we were able to get all the y's on one side, all the t's on the other. The other way to see that it's separable is we said it has to be a product of a function of y and a function of x, or again in this case a function of t. And so we could look at this as being t over t plus 1 times y. So it is a separate product, a product of one variable, a function of one variable, and then a function of another variable. Okay, last one over here. So this one is not immediately obvious. You have to apply some exponent rules on this one. So we have dy dx equals e to the x times e to the y. We know that if you have a sum of exponents, you could write that as a product of two exponential terms with the same base. Now you can see it is a product of x, a function of x, and a function of y. So this one is separable. Let's go ahead and finish the separation though. So we would divide by the e to the y, so it would be dy over e to the y, and then we can multiply the dx over e to the x dx. We've separated completely the x's and the y's, so this one is separable. Okay, let's see how this actually can be applied to solve a differential equation. So in this example, it is separable because you have a function of y multiplied by a separate function of t. So we're going to get all the y's on the left and everything with t on the right. So when we separate, it will be dy over y squared equals e to the negative t dt. So all I did was divide the y squared over and multiplied the dt to the other side. We've separated the variables, so now we can take the antiderivative on both sides. So on the left, we're integrating with respect to y. On the right, we're integrating with respect to t. This one could be written as y to the negative 2 dt, or sorry, dy equals, we'll just leave that one the way it is for now. Okay, so antiderivative here, we need to increase the power by 1, and then we divide by that new power. Technically there is a plus c here, but we're going to get a plus c on the right hand side, and we'll eventually just combine them, so we can just have one arbitrary constant. We don't need to write two separate. Okay, so this one, antiderivative of e to the t is just e to the t, but we have that negative in front of it, which means we're going to get a negative out in front of this. Technically you're doing a substitution there, u substitution, but we should be able to see through that one without actually doing the substitution. Okay, so we're almost done. Let's multiply the negative over. So this would be y to the negative 1 equals e to the negative t plus c. And you might say, well, you missed the negative. You should have put a negative here. Well, negative 1 times a constant is still a constant. If you want to have this as minus here, you can, but it doesn't actually change the general solution. Minus c is the same as plus c. Okay, so then we need to deal with the negative 1 exponent. So the easy way to do that is take both sides and raise it to the negative 1 power. Here you would multiply those powers and they would cancel, or negative 1 times negative 1 is positive 1, so we just end up with y equals this, but we could write that as 1 over e to the negative t plus c. If you didn't like that argument, then another way to see this is the left-hand side is just 1 over y, and then to finish it, we just need to take the reciprocal of both sides. Flip this side, flip that side, and that gives you this. So this would be our general solution. Every solution to this differential equation should have this form. Now we want to find the value of this arbitrary constant by using this initial condition here. So we know that y of 0 is equal to 1 over e to the 0 plus c, but that would just be 1 over 1 plus c. And we were told that this is 1/2. So 1/2 is equal to 1 over 1 plus c. If you cross multiply, then you have 1 plus c equals 2. Subtract this over, c is equal to 1. So putting this back in gives us our particular solution. Y of t is equal to 1 over e to the negative t plus 1. And that's it. That's our solution for that first one. All right, we're going to skip most of the quick checks, but let's do this first one here. So this says write this in separated form. So another way to write the left-hand side would be to say dy dt. That's what y prime is. And the right-hand side is just t squared plus 1 over y cubed. This one is set up just like a proportion, so we could immediately multiply the y cubed over here and the dt over here. So you'd have y cubed dy equals t squared plus 1 dt. It's in separated form. It's ready for you to go in and integrate, but it didn't ask us to finish solving it. Okay, so in the box here, I just have all of the general steps for solving a separable differential equation. First step is separate the variables, as we've been saying. So if you have a product of x, function of x, and a function of y, you're going to divide by the function of y, and you're going to multiply the dx to the other side. Then in step 2, you get to just integrate both sides, left-hand side with respect to y, right-hand side with respect to x. When you integrate, you technically get constants on both sides, but you can just combine it, as it says here, into one single arbitrary constant on the right side. And then if it's an initial value problem, you just use the initial value to find the value of the arbitrary constant. So let's try another one. So we've got our differential equation here. You can see it is a function of y times a function of x. So let's go ahead and separate this. So we have dy divided by e to the negative y equals sine of x dx. So we've separated the variables. But notice we could simplify this. E to the negative y, it's already in the bottom. That brings it up to the top. So this is really e to the y dy equals sine of x dx. All right, now we're ready to integrate, take the antiderivative of both sides. So antiderivative of e to the y is just e to the y. And again, we don't need to put the plus c because we'll put it over here. Antiderivative of sine is going to be negative cosine of x, and then we'll put the plus c. Remember, derivative of cosine is negative sine, so we had to put this negative to cancel that out. So this is our general solution. It is currently written, it's implicitly defined in terms of y. So it is technically considered the solution, but to get the actual y function, we would need to solve this for y. And we can do that by taking a natural log of both sides. If we take ln of e to the y, that is equal to ln of negative cosine x plus c. Over here, that's going to cancel, leaving you just with y equals ln of negative cosine x plus c. Okay, so that's our general solution. And they said take the general solution and solve those initial values. So let's do this on a separate page. Okay, so I've just put the general solution up here, give us more space to solve these initial value problems. So let's start with the y of 0 is equal to 1 case. So let's do y of 0. Plugging into this would be ln of negative cosine of 0 plus c. Cosine of 0 is 1, so we have negative 1 plus c, and y of 0 is supposed to be 1. So then we can exponentiate on both sides, so e to the first should be equal to just negative 1 plus c. You can think of that as just being the definition of a log, or we came back here and we exponentiated both sides, and using the inverse properties, those would have canceled. So then we just add this over, you get e plus 1 is equal to c. So for this case, we end up with the solution of y is equal to ln of negative cosine of x plus e plus 1. Right, that would be the solution for this initial condition. Okay, let's try the next one. Put that in here. So we have y of pi over 2 equals, plug pi over 2 into that, ln of negative cosine pi over 2 plus the constant c. And this time cosine of pi over 2 is going to be 0, so we would just end up with ln of c there, but we're supposed to get out 1/2. Again, exponentiate both sides. E to the 1/2 would be c, or in other words, c is the square root of e. So the solution we get in that case is ln of negative cosine of x plus the square root of e. So I've got our first one, second one, and then we'll finish with that third one there. So this is y of 0, supposed to come out to negative 3 this time. So we know when we plug 0 in, we can go straight to that form there. We know it's ln of negative 1 plus c, but it's supposed to be equal to negative 3 this time. So negative 3 equals ln of negative 1 plus c. Exponentiate both sides. So e to the negative 3 is equal to negative 1 plus c, and then you can add the 1 over. So e to the negative 3 plus 1 is c, giving you a final solution of y equals ln of negative cosine of x plus e to the negative 3 plus 1. Okay, let's look at these three solutions graphed for this differential equation. Okay, so here we have our three solutions that we found. This was the first case, the first initial condition. You see the blue curve here following the slope field. Then the green one. And then you get the red one in there as well. All matching the slope curve that we see there, or the slope field. So nothing we needed to do with this, just thought it was a nice looking picture to include here. Okay, let's move on to the next one. Okay, so this says find and graph the solution to the initial value problem given by this. It's almost separated for us. We just need to move the dt to the other side. So let's go ahead and do that. Let's go back to blue. Alright, cosine of y dy equals sine squared t cosine t dt. So variables are separated, so we can now integrate on both sides. So on the left hand side, the antiderivative of cosine is just sine of y. And again, we'll put the constant on the other side. Over here, we're going to need to do a little substitution. So we're going to let u equal sine of t. So then du would equal cosine t dt. So making that substitution, that could be written as u squared du. So all of our integration techniques, they still apply here. Those rules could still work. Okay, so we have sine of y equals, antiderivative of that would be u cubed over 3 plus c. But we want to put back in the sine of t for u, so this turns into sine of y equals sine cubed t over 3 plus c. So this is our general solution, but we want to solve the particular solution with this initial value. So one thing to notice on this, it would not be considered a great idea to solve this for y. You could try taking sine inverse of both sides, but remember that sine and sine inverse don't actually have, sine is not a one-to-one function. So if you take sine inverse, you are restricting its domain down, and we don't want to do that. So we would typically leave it like this. This is an implicitly defined function. And in fact, I have the graph of what this looks like over here. you can see it actually consists of infinitely many branches here. And so we just want to find the particular branch that gives us this initial condition. So let's go ahead and solve this for y, or sorry, solve it for the c value. So we're going to plug in 0 in for t and this in for the y. So over here we are going to do sine of pi over 6, because if we plug 0 in for t, the y has to be pi over 6, and that equals sine of 0 all cubed, because that's what that notation really means, divided by 3 plus c. Well, sine of 0 is 0, so this whole thing is just going to get wiped out. Sine of pi over 6 is going to be 1/2. So 1/2 is what our c value is. Okay, so our particular solution then is sine of y equals sine cubed t over 3 plus 1/2. And we just leave it in that form, right? This is an implicitly defined function, which is perfectly acceptable to just leave it in that form. I had GeoGebra graph that for us here, and so it actually gives you all of these different branches. Okay, so we're going to revisit a problem from the previous set of notes. We looked at the logistic function that modeled population growth up to a certain carrying capacity. This was the exact differential equation that we had. In that set of notes, we created the slope field for that curve. And it was one that we could do pretty easily because there was no t on this side, so that meant that all of the slopes across horizontally were all the same thing, all the way across. We could just copy it over and over all the way across. Okay, so this is a separable differential equation, but it is kind of a monster, so buckle up. This one's going to be a pretty long one here. Let's read the problem. It says, assume 50 fruit flies are in a large jar at the beginning of an experiment. Let P of t be the number of fruit flies in the jar t days later. At first, the population grows exponentially, but due to limited space and food supply, the growth rate decreases and the population is prevented from growing without bound. This experiment is modeled by the logistic equation, which we have here. And then it says, together with the initial condition of P of 0 equals 50, solve the initial value problem. So right here, we're saying P of 0 is 50. That means we already have the solution curve actually graphed right here. This red one that we see is the solution curve that we're trying to find the formula for. Obviously, it's just an approximation. We're just trying to follow the slope field there, but we want to do all of the math by hand here. Okay, so the first thing we have to do is separate the variables. So what I'm going to do is I'm going to take this part here, because all of that involves P. I'm going to take that to the other side. So that's going to be dP over P times 1 minus P over 300 equals, I left the 0.1 on this side, and then I'll put the dt there. So multiply dt here, divided this to the other side. Okay, so now we're going to clean up that fraction a little bit. So I don't like having compound fractions, so what I'm going to do is multiply the top and the bottom of this one by 300. And I will actually distribute that 300 through the parentheses. So that will turn into 300 over P times 300 minus P. I'll just keep the dP over here on this side. So now that's just a cleaner expression. Okay, so we want to integrate, but the problem is we don't know how to integrate this expression, and we can't actually do a substitution on that, so we need something else. So we're going to have to remember something all the way back from college algebra. In college algebra, we took rational expressions like this that were considered proper fractions, meaning that the degree of the top is less than the degree of the bottom. Degree of the top is 0, degree of this is squared, and we split it up into separate fractions where the factors, the denominators were the factors of the original, meaning that one denominator was P, the other denominator was 300 minus P. When we did this, we said, okay, well, this has to be some number, and that has to be some other number. So this was called partial fraction decomposition. Technically, this is something that was supposed to be reviewed in Chapter 7, the chapter that we skipped, but this is a pretty easy one, so I think it's, at least the decomposition part's easy, so I think it's okay to review it right here. Okay, so the strategy for partial fraction decomposition is you multiply everything by this denominator. So the left-hand side would just be 300. When you multiply this factor by this, the p's cancel, so you get just a times 300 minus p. And then when you multiply these two, the 300 minus p's cancel, so you just get b times p. So then what we try to do is pick convenient values for p that will wipe out either a or b. So the first one to choose would obviously be p equals 300. If we set p equal to 300, this is going to get wiped out, and you would just get 300 equals 300 times b. Right, plugging 300 in here will make that 0, so this gets canceled. So this 300 would have to equal 300 times b, which means b is actually equal to 1. So we know back here that's actually 1. Okay, the other value we should use is 0, because that would wipe out this term here. So that would give us 300 is equal to, plug 0 into this, you'd have a times just 300, because it'd be 300 minus 0. That was wiped out. Divide this over, and again you get a is equal to 1. So what we've shown here is that 300 over p times 300 minus p is equal to 1 over p plus 1 over 300 minus p. Now, how is that useful to us? Well, remember, we wanted to integrate this, which means we could just integrate this. And at first you might think, well, that's worse, that's not better, but actually we can integrate both of these fairly easily. Before I integrate, let's look at this one a little bit more closely. You don't have to do this step, but I think it makes it better. I'm going to factor a negative out of the bottom, which will flip this around, and I'm just going to put that negative, actually I can just put it right here. So this is the same as doing the integral from the integral of 1 over p minus 1 over p minus 300. Right, that negative, if you distribute it back down through that denominator, would take you back to this. Okay, so that antiderivative then, this one would be ln of the absolute value of p minus ln of the absolute value of p minus 300. Okay, so normally you'd have a plus c here, but remember, we had, if we go all the way back up, the right-hand side was this thing. So let's bring that back down. So we need to integrate that side. That's just going to be 0.1 t plus a constant c. Okay, so that's our solution. Let's actually get rid of the equal sign right here. So this is our solution to our differential equation, but we really would like to solve this for p. This is where it starts to get a little nasty, so stick with me here. First thing to notice is we have a difference of logs, so that can be written using a property of logs as a quotient. If you have a difference of two logs, it can be written as the log of the quotient. Okay, the next step is we're going to exponentiate both sides. So this would, if we exponentiate, meaning do something like this, then this is going to cancel, leaving just the absolute value of p over p minus 300 equals e to the 0.1 t plus c. Now the critical thing right here is that this c is in the exponent. This is usually where the mistakes are made. When they exponentiate, people try to put the e here as well, and that is not true. That's not how that works. So it has to be up in the exponent. But I don't really like leaving it there. So another way to write this would be, it's a exponent that has a sum, so you could write it as e to the c times e to the 0.1t. We have the same base. When you have the same base, you can add the exponents, which is exactly what this says here. Okay, now this is, c is any arbitrary constant. So if I take e and raise it to the c, that is also just an arbitrary constant. But over here we have the absolute value. So if I wanted to get rid of the absolute value, what we would have to do is put plus or minus in front of this. Right, this right now is always positive, but having the absolute value over here means this could be negative. So if I want to get rid of it, I'd have to write it like this. But, and this is where it starts to get a little strange, c is an arbitrary constant, which means e to the c is pretty much an arbitrary constant as well, and now we've also said it could be plus or minus, it could be anything. So this whole thing is just another arbitrary constant. So what we often do, and this usually drives students mad when we do it, but we just write that whole thing as c, because it is just some arbitrary constant. It could be positive or negative, so that doesn't matter. E to any constant, you can make that any number you want, so you might as well just write this as c times e to the 0.1t. Okay, so now the next thing is not a step that would have to be done, but if we're going to make this solution match what's in the book, then what I want to do is take the reciprocal of this side. So if I take the reciprocal of that, it'd be p minus 300 over p. I have to take the reciprocal of that side, so it would be 1 over c e to the 0.1t. But I don't really like the way that's written, so what I could do is I could write this as 1 over c e to the negative 0.1t. Right, this is down in the denominator, so if I just want to bring it back up, I put a negative in the exponent. And we're going to play some games again here. 1 over c is an arbitrary constant, so really I might as well just write that as c. So we've got p minus 300 over p is equal to c times e to the negative 0.1t, because that whole thing is just an arbitrary constant. Okay, we're getting closer. So now we want to solve this for p. To do that, we would need to get all the p's in the numerator and on the same side. So we're going to multiply this p over here. So we have p minus 300 equals p times c e to the negative 0.1t. And let's subtract this to this side over here. So we have p minus p c e to the negative 0.1t. And if you don't mind, I'm going to go ahead and add the 300 to the other side. Okay, so then we have all the p's on one side. We can factor it out. So it's p times 1 minus c e to the negative 0.1t equals 300. And then we can just divide this over. So p equals, oh, somehow I got 3,000 there, 300 over 1 minus c e to the negative 0.1t. Okay, and this is our solution, but if we're going to make it match the book exactly, they play the game again. Minus a constant is the same as plus a constant, so I believe they keep it in the form 300 over 1 plus c e to the negative 0.1t. It does not make a difference. It will work out the same way in the end, either way. It's just that, if you left it this way, our c would come out negative, where if we leave it this form, the c, as we will see, is going to come out positive. So really they are the same equation since c is an arbitrary constant. Okay, so we've got our general solution. Somewhere back up here we had an initial condition. I'll just keep this here and bring it down. Our initial condition was p of 0 is equal to 50. Okay, so let's do that. P of 0, plugging 0 into this, would be 300, keep wanting to write 3,000, over 1 plus c e to the 0. That whole exponent would be 0. And that's supposed to equal 50, so we'll put the 50 over here. P of 0 is supposed to be 50. So 300 over 1 plus c, because e to the 0 would just be 1. We can multiply this to the other side, so 50 times 1 plus c equals 300. You could distribute, but I'm going to go ahead and divide. 1 plus c is equal to 6, and then subtract over, c comes out to 5. So this gives us our particular solution of p of t equals 300 over 1 plus 5 e to the negative 0.1 t. Okay, so that's a long one. It is an important one. It's one that's used quite a bit in the science field, so it's going to be longer than most of the ones you do in your homework, but I wanted you to at least see that done fully in one example. Okay, I think we have another application. And I believe this is our last one. So this is Newton's law of cooling. It states that Newton's law of cooling is based on the fact that heat flows in the direction of hot to cold. So Newton's law of cooling says that the rate at which the temperature of an object changes at any time is proportional to the temperature difference between the object and the ambient temperature at that time. Ambient temperature meaning like the room temperature. Now this statement transforms directly into this differential equation. If you remember, when we say things vary proportionally, we mean that's the same as saying they vary directly. So direct variation, y varies directly as x, says that y equals some constant times x. So that's where this is really coming from. Except they're not saying y, they're saying the rate of change. It says the rate of change in temperature with respect to time, this, varies directly as the difference in the temperature and the ambient temperature. And then here is just our arbitrary constant in front. They've put a negative in front of it. That really doesn't matter. It doesn't change anything, but this is direct variation. The rate of change in the temperature varies directly as the difference in the temperature at time t and the ambient temperature. Okay, so let's try applying this. So it says solve the differential equation. We have no initial condition at the beginning. We're just solving the general differential equation. So we need to get, and this is really annoying because you got t, capital T and lowercase t. We need to get capital T on one side and lowercase t on the other. Now you'll notice you see this little t here. This is just representing the argument of that function. It really doesn't need to be written there at all. It's just reminding you that capital T is a function of lowercase t. So for us, it's going to be better to actually think of it like this. Now that might seem weird. Why are we allowed to do that? Well, we were doing that on every problem. If we come back to, I need to go back further. Okay, if we come back to even something like this, this technically should have been written as t squared plus 1 over y of t all cubed. The implication was that y was a function of t. We just suppressed the argument on all the other problems. We didn't write the input for the function. Okay, so that's all I'm doing. I'm just suppressing that. It doesn't need to be written there. So to separate this, we can divide this expression over. So you have d with capital T over capital T minus a equals negative k dt with a lowercase t. So we've separated the variables. We've got the capital T on one side, lowercase t on the other side. And now we can integrate. So on this side, this is going to be natural log of the absolute value of t minus a. And on the right hand side, that's going to be negative k t plus c. Technically, to get this, I was doing a u substitution. I was setting u equal to t minus a, but if you do that, if u equals t minus a, then du would just be capital T, would just be capital dt, because the derivative of that would just be 1. So that's why we can kind of skip doing all those steps. Okay, so this is our solution, but we would like to get it solved for the capital T. So like the previous one, we are going to exponentiate again, and remember that the c is up in the exponent there. All right, so these cancel. You'd get absolute value of t minus a equals e to the negative kt plus c. And we're going to do a lot of the same tricks that we did with the last one on this. So I'm going to rewrite the right-hand side as e to the c, e to the negative kt. We can put plus or minus in front of it, which enables us to get rid of these absolute values that we have here. So it would just be t minus a then. But this is just an arbitrary constant, so we could just rewrite that as c again, c e to the negative kt. And I know that's the part that probably is going to take the longest to get used to, but there's no t in that. E to the c, that could represent any number, so we might as well just relabel that as c. Alright, and then we can add the a to the other side. So t is equal to c e to the negative kt plus a. And so that is our solution. This is now a function of just t. That is the general solution. Okay, I think the quick check after this is saying what do you, like, if this was our solution that we had, what is the c value if we set the initial temperature to be T naught? So let's just solve that. So T of 0, plugging into this, would be c e to the 0 plus a, but we're saying let T0 be T naught, meaning the initial temperature. E to the 0 is 1, so this would be c plus a. Subtract over, c comes out to T naught minus a. So that gives us the particular solution of T naught minus a times e to the negative kt plus a. So what is this telling us? Well, it gives us, like, we can see exactly what this constant represents. It's simply the difference between the initial temperature of the object and the ambient temperature. So you take that temperature difference, that's your coefficient, you put your ambient temperature out here, and then the only other thing to find is this k value. The k value is going to depend on the conductivity of the object that you've heated or cooled. How conductive it is going to change the value of k. So let's try applying that. So this says a bowl is removed from a pottery kiln at a temperature of 200 degrees Celsius and placed on a rack in a room with an ambient temperature of 20 degrees Celsius. 2 minutes after the bowl is removed, its temperature is 160 degrees. Find the temperature of the bowl for all time t. So we don't have to redo the whole differential equation. We've solved it in general. When an object is cooling, we know that its temperature is modeled by that function there. So, and we have most of the information for this. For example, we know that the initial temperature of the object was 200. We know that the ambient temperature in the room is 20 degrees Celsius. And we also know that if we are to plug 2 into our function, we get out 160. So let's put these two things in first. So this tells us that our function t of t is 200 minus 20, which would be 180. That's the difference in the starting temperature and the ambient temperature. E to the negative kt plus ambient temperature, which is 20. Okay, so the last thing to do is to figure out what is this value of k. To do that, we can use the initial condition. So let's go ahead and put that in. So we know that if we plug in 2, we get out 160. So this would be 180 e to the negative k times 2. We're plugging the 2 in for the t plus 20. So we're solving this for k. Subtract this over, you get 140 equals 180 e to the negative 2k. Divide the 180 over, and reduce that, you get 7/9 equals e to the negative 2k. Take a natural log of both sides. ln of 7/9 equals negative 2k. And then divide over by the negative 2. So k will come out as ln of 7/9 divided by negative 2, which is approximately 0.126. And then we just plug everything back in. So our function modeling the temperature of this object would be 180 e to the negative 0.126 t plus 20. Alright, and that's that. I believe that's the last example and the end of this section. So hopefully that was clear. If you do have any trouble with the homework problems, make sure you're emailing me, and we'll see you guys in the next video.